Okay, so looking a little bit at how the chemistry works in terms of a graphical analysis. If you look, you can see that all through, for the most part of the time that chlorofluorocarbons were used, the ozone concentration stayed pretty high. It wasn't until the 70s that you started to see a decrease. Well, this is something known as lag time, and it often is shown, unfortunately, many years after the negative impact occurs. So we start to see right around the 1970s a significant decrease in the amount of ozone that's being measured in the atmosphere. So as a result of this, right around this point, scientists started to become concerned, and in 1987, I've mentioned this a couple of times, we adopted the Montreal Protocol, and I'll talk about that again a little bit more in a couple of slides. But lag time is frequently something that we see in ecosystems because it just takes time for the effects to be able to be measured. And given that chlorine can destroy quite a bit of ozone, that's why we start to see this, is it took time for the amount of chlorofluorocarbons in the atmosphere to start to deplete the ozone to the point where we could measure this. And I'm sure that you've seen images like this before. And again, the ozone hole has nothing to do with climate change. I've said it before, and I'll continue to say it several more times. But the climate change deals with carbon dioxide and the insulating effect that carbon dioxide has, whereas the ozone hole specifically deals with O3 and the depletion of O3 in chlorofluorocarbons. There are certain times of the year when chlorine, as you guys know from chemistry, that heat will increase the rate at which reactions occur. So ozone depletion is a little more seasonal, and it happens when this reaction, which is enhanced by the opposite of what you know, it's enhanced by cold temperatures. So usually the hole in the ozone is a little bit bigger during the winter months than it is over during the summer months. So what you see here is kind of the outline of the hole. And again, seasonally, this will increase and decrease depending on the temperatures. The greatest depletion of ozone happens at the poles, simply because this is where it's coldest. And again, this reaction runs best during cold temperatures. However, the really good news is that the ozone hole, and again, if you notice, this was taken in 2000, the ozone hole, even at its biggest, at present day, is about that size. So the Montreal Protocol, which I've mentioned several times, which was passed in 1987, is actually doing its job. There were multiple nations that committed to reducing CFCs, and then once 2000 came, the phase out continued. The whole idea behind this was to completely phase out 96 ozone depleting compounds. The nations that were involved with this were all were all developed countries, but they are the primary users of chlorofluorocarbons. So keeping in mind that it does take a while for CFCs to leave the atmosphere, to run through that cycle of breaking down ozone, since 1987, you saw go back, take a look, you continue to see a decrease, that lag time effect into 2000. But since 2000, there has started to be an improvement in terms of the size of the ozone hole and how long it's there. So the Montreal Protocol is a perfect example of when an entire set of nations work together towards a common goal, that there can actually be environmental problems that are solved. All right, so this little diagram, this is right from your textbook, and it nothing more than just a summary of the criteria, air pollutants, their symbols, where they come from, and then effects that they have. You may want to spend a little time glancing over the effects. It does a little bit better job in this particular table than I did. I didn't spend a lot of time other than just saying it was a respiratory irritant a couple of times, but the table does a really good job of kind of summarizing the impacts of each of the air pollutants. All right, you did the acid deposition lab. And in looking at this, this is any type of precipitation that has a pH lower than 5.6. So this could be fog, this could be snow, and this could be rain. Remember, we've talked about this before, that water and carbon dioxide lower pH from neutral anywhere to something that's acidic. Not just carbon dioxide involved here, but I also want you to realize that it's sulfur and nitrogen oxides as well. So both SOx and NOx, as well as carbon dioxide, play a role. If you'll notice, the chemistry to this is very well laid out in this diagram. For the most part, the one thing you need to add is water, and then you end up with both the sulfuric acid and the nitric acid, which will dissociate to form those hydrogen ions, and those hydrogen ions are the things that will increase, will lower your pH when they fall into the waterways. These two things, the sulfate and nitrate, are salts, and I mentioned this previously, but those salts will increase the salinity of waterways as well. So consequences of acid deposition. As you guys know from visiting Darby Creek, a lot of organisms only live in optimal pH ranges. Those very sensitive indicators don't live very far outside of this 6.5 pH. So even a little bit of acidification for very sensitive organisms can cause problems. Salamanders just can't survive in pHs lower than 5. The acid precipitation, when it falls on trees, especially spruce trees, and some trees that are already struggling with things like pine beetles and ash borer, the precipitation will wear away the waxy part of needles, the waxy part of leaves, leaving the organism or the trees susceptible to all types of different diseases and pests. It also has effects on, so there's an example of what I was talking about in regards to the leaves. This is acid deposition on a car. Acid rain also makes certain organic materials more soluble. Two examples of those would be mercury and lead. Both mercury and lead are found in soil naturally, so acid precipitation falling on soil, and again, you may want to write this down just if you're not going to remember it, but acid precipitation falling on soil makes that mercury or the lead more soluble, and as a result, the mercury in particular will form methylmercury, which will accumulate in fish. Acid rain can definitely have some consequences in terms of releasing mercury into waterways and exposing fish to it. In addition, it also leaches calcium and magnesium from soil. Both of those are required soil nutrients for plants to grow. So sulfuric acid can have some long-term effects both on soil fertility and on the solubility of things that you find in that soil. Just a couple of those pictures, in a little bit bigger view. Also, too, acid deposition, as you should realize from the lab and looking at chalk, it has consequences over time, and that it wears away marble statues. Marble and chalk are closely related in terms of composition. So you can see that, this particular statue has had some acid deposition wear that is definitely affecting it. All right, another air pollution phenomenon that you should be familiar with are called thermal inversions. In normal conditions, as you notice, you've got warm air, and then you have cool air, and then you have cooler air above that. So the warm air is closest to the city, as you would expect it to be, simply because there's all types of black materials that are used in a city that will absorb heat. The other thing that you see here is that this is kind of sit in a basin. So thermal inversions typically are specific geographic phenomenon. Areas that kind of sit in low-lying areas have these types of problems. If you look at the graph to the right, you can see that temperature tends to increase as altitude decreases. So the closer you are to the Earth, the warmer the temperature is. In an inversion, though, on the other hand, if you notice, you have cooler air that's trapped underneath a warm layer of air, and then even colder air above it. So as a result, if you notice the graph again, you start to see that temperature increase with altitude decrease, and then all of a sudden the temperature decreases as altitude continues to decrease. So as a result, what happens is that this relatively warm layer of air that you see traps that cool air and all of the pollutants underneath it. So this is, usually places where you have a valley surrounded by mountains, and you'll end up with this type of phenomenon on a frequent basis. On the other hand, if you have areas that you have a sunny climate with light winds frequently, usually coastal cities very rarely will have thermal inversions because they won't be surrounded by mountains all the way around the city. And you'll continually have sea breezes that come in that kind of prevent this inversion from occurring. Probably one of the best known places, again, in the United States, if it's not well known enough for other problems that it has for thermal inversions, is Los Angeles. Los Angeles sits in a little basin. Unfortunately, the basin prevents airflow, and it's warm enough that frequently they end up with this type of setup that occurs. However, just for your own that thermal inversions also can happen in everyday places like Ohio as well. Air quality alerts don't always happen in the summer. Fog and low visibilities in the mornings are also caused by a temperature inversion that occurs. So kind of keep in mind that whenever you see fog and some of those low visibility mornings, that very well this could be caused by a temperature inversion that has happened in the area. This particular picture does a wonderful job of showing you what a thermal inversion looks like. You can literally see through here where the different temperatures occur. If you again look at the previous slide, this air is going to be cool air. This warm air has this trapped, and then there's cooler air above it. So in this instance, you can actually see, you can see the mountains in the background. What you can't see behind you is like another set of mountains that kind of have this entire area all encased in a little bit of a bowl type depression. All right, so how do we get to the point where we can help control some of these pollution issues that we have? We can use low sulfur coal if that's an option. We talked about this a little bit at the beginning of the year, but most of the power plants in the eastern part of the United States ship coal in from the west. West has low sulfur coal in comparison to the eastern part of the country. And power plants can mix in that low sulfur coal, and it means that, yes, they're still releasing sulfur, but they don't have to go through the scrubbing process, and we'll talk about that in a minute, of removing as much sulfur at one time. Removing the sulfur dioxide from exhaust is that scrubbing process that we'll talk about in a second. You can burn the coal at lower temperatures. It doesn't release as much sulfur at one time. However, the problem with that is that you don't necessarily get the same energy output. And then using catalytic converters in automobiles has helped reduce the amount of nitrogen emissions in cars. So you should be very familiar with how this works. Okay, scrubbers can remove 98% of SOx compounds from coal emissions. However, they're really expensive. All right, so in order to use these, the coal companies have to front quite a bit of money to put these in their smokestacks. They are not super good at removing fine particulate matter or ultra particulate matter. They will get a little bit of the larger particulate matter, but not the super big stuff. All right, so super easy diagram to follow. Dirty air inners, as you can see at number 1. You take that combustion exhaust and it kind of rain on it. So this uses water. This is scrubbing water. And basically what happens is that mist collects the particles and it brings them to the bottom of the unit. Down in number 3, this dirty water then moves to a sludge removal system, and this sludge has to be cleaned before the water can be reintroduced into whatever its original source was, and then the sludge has to be disposed of, usually in some type of special facility, because again, burning coal is associated with mercury in some places. So that sludge just can't go to a typical landfill facility. The air that comes out is free of sulfur, and as a result, you end up with virtually no sulfur that's being outputted into the atmosphere. Okay. The other option is using an electrostatic precipitator. An electrostatic precipitator really focuses on removing particulate matter. Some of the downfalls to this is that it does require a huge amount of electricity to use it. The dust that's collected from it does have to be disposed of because, once again, it's toxic. It could have mercury in it. And it doesn't remove ultrafine particle material either. It only gets that fine particle material in between. So again, this just uses electricity, uses charges to collect the particulate matter from the dirty air, and you can see on the right-hand side that you end up with clean air. At some point, the electrostatic precipitator will be turned off. There'll no longer be an electric charge, and all the particles that you see that are stuck on the electrodes will drop into the hopper and then be disposed of. So primarily using scrubbers, again, is where the sulfur is removed. Electrostatic precipitators remove particulate matter. Okay. So 2 options that are used today to help keep the air that comes out of coal burning power plants a little bit cleaner. All right, so we want to talk about indoor air pollution. That's the last topic for this chapter. And believe it or not, indoor air pollution causes more deaths than outdoor air pollution. And if you'll notice, probably not a surprise, but this is more so in developing countries than it is in developed countries. Most of those kids are less than 5 years old. Keep in mind, back from the chapter where we talked about environmental health risks, children have, lower immune systems to start with. In developing country, these kids are probably fighting off malaria or a host of other waterborne illnesses. So as a result, indoor air pollution just becomes a bigger issue for them than for us. The other thing is that in the homes that they have, there's not a whole lot of ventilation. So as a result, you're not going to remove those indoor air pollutants like you would out of your house. If you've ever seen your furnace filter changed, if not, be sure you look the next time your parents change it. But that furnace filter in and of itself, your furnace moves air throughout your house, and that filter catches some of those indoor air pollutants in it, and then you dispose of it. In a developing country, they don't have a furnace, let alone a filter. So there's no way to move air and keep it ventilated. In looking at this, you should be familiar with a couple of different sources of indoor air pollutants that you could be exposed to. Probably one of the big ones is radon from rocks and soil underneath a house. If you haven't already, talk to your parents, ask your parents if you have a radon detection or a mitigation system in your basement. In some parts of Franklin County and Union County and Delaware County, the soil that is in this area has a large amount of radon in it, which over time breaks down and can cause cancer. So really the only mitigation thing is just to make sure that there's a fan, and most of the time the air is constantly ventilated in the basement. Carbon monoxide from your furnace, making sure that your wood stove, and most of you probably don't have a wood stove, but that your gas water tank or whatever is well vented in your basement. Fireplaces, even though they're wonderful, introduce particulate matter into your house. House products, paints, pesticides have VOCs in them. Cleaning fluids have VOCs in them. Furniture and carpet, again, a lot of those things have VOCs in them to make them water resistant or stain resistant. If someone smokes in your house, again, carcinogens and other toxic compounds will be held in the house as well. Right, so looking at 4 different groups of indoor air pollutants: asbestos, carbon monoxide, radon, and VOCs. Okay, asbestos is not something that you will find used in houses purposely anymore today. This is, again, an older home issue. It was mainly used as insulation and mostly in pipes. So if you're ever in an old house and you're in the basement, kind of look at the pipes that are overhead. And a lot of times they'll kind of have like a gray mat to them or a white mat to them. There's a really good chance that they may have asbestos in them. Also, older tiles that go on the floor many times will have asbestos in them as well. As long as those fibers are not disturbed, all is fine. So if asbestos is found in your house, it could potentially not be a problem, just as long as you don't try to remove it. The big danger becomes from the really fine fibers when asbestos is trying to be removed. Asbestos generally is related to lung cancer, so just kind of keep in mind that it does have consequences. But again, today it's very expensive to have removed. It can be removed safely from older houses. And it's also completely safe as long as it's not disturbed. Radon occurs naturally from the decay of uranium. So uranium is radioactive and decays into radon. And again, the uranium can be found, again, in some of the soils and rocks in and around Franklin County, Delaware County, Union County. And the only thing that you have to be aware of is that it's there. So if you haven't had your basement tested for radon, it might be worth having it tested. And then mitigating for it, most of the time just involves a fan, making sure that that air from the basement is constantly removed to the outside. It's the second leading cause of cancer in the United States. So it's definitely something that you want to be careful of. In addition, radon can also be associated with granite. So many times the granite, depending on where it forms, will have uranium in it. That uranium will decay over time. And so if you think about it, granite's on countertops of both your sinks and your kitchens. A lot of times it's worth just having those areas also tested to make sure they don't contain radon as well. We've already talked about carbon monoxide. Basically, this is due to incomplete combustion of some type of fuel or heater. So this exhaust escapes into the living area. If the area is not well ventilated, remember this is colorless and odorless, it can build up and basically causes suffocation because it binds to hemoglobin and prevents hemoglobin from picking up oxygen. The last indoor air pollutant are volatile organic compounds. They're used in a lot of home products: glue, paint, furniture, flooring. It's also used in formaldehyde. So a lot of these products are used definitely for waterproofing or to make fibers more resilient. But again, they're not an issue as long as ventilation is well taken care of within the home. As long as your home is ventilated, then you usually don't have any issues that you need to worry about in that regard. So with volatile organic compounds, as with most of the indoor pollutants that I just talked about, they're not a huge concern because your home is well ventilated. However, if you were to visit a developing country and spend an extended period of time in their homes, you need to keep in mind that ventilation is not going to be anywhere close to what it is that you experience in this country in your home.